first speaker is Eamonn Connolly. Eamonn is the Director of Engineering at James McHugh Construction. He earned his Bachelor of Science in Civil Engineering from the Illinois Institute of Technology in Chicago and his Master's of Philosophy and Engineering from the University of Aberdeen in Scotland. He's a licensed structural engineer in Illinois and a licensed professional engineer in 7 states. He's active with committee memberships in numerous professional organizations, including ACI, ASCE, PTI, SEAOI, and SEF. Eamonn has over 20 years of extensive and wide-ranging experience as a structural engineer and manager in the design and construction of numerous high-rise buildings and infrastructure projects. He's going to be discussing what are we going to pump that with. Eamonn?
Okay, thank you. Thank you for the introduction. Okay, well, anyways, thanks for everybody for tuning in. I look forward to hopefully be able to see you all in the flesh in a real convention soon. So with that, I'll begin. So what are we going to pump that with? It's a basic question that builders are confronted with. And I want to just basically run through some bits of information, some experience learned, and some various images and video. So hopefully you guys find this informative and interesting. So SOM, Stan Carista, had a good observation, and he basically said that what really makes the difference for concrete construction is the development of high-strength concrete mixes, the greatly increased efficiency of concrete pumps and placing booms, and the development of forming systems that can be erected safely and quickly, then move to the next location. So bluntly, he's saying that our ability to build tall, quickly, and economically is really a function of all this technology. And top of the list of technology that's critical is the concrete pumping technology and the concrete mix technology that goes with that. And there's 2 examples right there, the Trump Tower in 2009, as well as the Aqua project in 2009 also. And Aqua in particular is a really great showcase, just showing the fluidity of possibility with concrete with those wave inspired balconies. So what we hope to cover today with this presentation is discuss placing concrete on high-rise projects, and basically discuss logistical and engineering challenges, talk about some various methods and strategies to getting concrete efficiently to where it needs to go, and present some equipment and challenges and solutions. So just quick overview of the topic, and hopefully, share some insights. I think I would be remiss without pointing out to and directing all our viewers to a really great document. There's a guide to placing concrete by pumping methods by the ACI Committee 304. Definitely been a reference tool for me over the years and for preparing this presentation. So definitely check it out, and great appreciation for their work in putting together the fine document. So here's a good picture. If you're Chicago or from Chicago or Chicago native, you might appreciate it. This is an archive photo from 1923 from the Metropolitan Water Reclamation District. Basically, this is a bunch of workers constructing some wastewater treatment facility, I think out in Stickney. But what you see there is a whole collection of people with Georgia buggies transporting concrete from wherever it's batched to wherever it needs to go. So concrete being what it is, definitely it's heavy, it's awkward, and basically it caused great challenges for the early builders of concrete structures of taking it efficiently from where it was being batched to where it was being needed to be deposited. So obviously this is would definitely limit the use of concrete for different applications if this is the only way we could move it around. But really, modern concrete and modern conveyance of concrete really starts I think in Europe. So the first patented concrete pumps were, from what I could gather, were patented around the 1910s. 1913 was a patent I found out for Torcrete concrete pump in Germany. But the real big push happened after World War II and the rebuilding of Europe. The built environment was devastated by the war, and there was a great need, societal as well as economic, to build back quickly and rapidly, and that spurred on the motivation for new technologies. So here's 2 examples of early companies developed. Both Schwing and Putzmeister came out of that in Germany and have been basically world-class, world-leading ever since. So definitely necessity is the mother of all invention. Just want to discuss some different types of pumps. There are different types of pumps. There's pneumatic pumps. They're limited use primarily for shotcrete applications. You can see an example right here. It relies upon basically like a reservoir with basically compressed air pushing down on this reservoir and forcing out the concrete. And then there's squeeze pumps. There's an example of the motor here. They've got a collecting hopper, and then you have a vacuum pumping chamber with this rotary device with these wheels that would push on like a rubber hose that would basically be able to push out the material. It's low pressure, smooth flow. However, it's definitely a limited range distance and limited to highly flowable concrete or grout or cellular concrete or shotcrete. So kind of a limited use. But the primary workhorse, though, is the hydraulic piston pump. This is the most common, and this is what you'd see in any modern concrete operation. They can pump high volumes at very high pressures. For instance, this Putzmeister 14,000 here, McHugh has a couple of these. Has a rated capacity of 133 yards per hour, and basically an operating pressure of around 150 with a safety cutoff of 250. It can pump great heights and great distances in excess of 600 meters. My understanding is the current record for pumping is from the Burj Khalifa in 2008, where they were able to pump 606 meters at 200 bar. And they claim that, Putzmeister claims that they had reserve capacity getting, they could go even higher. So, the great, amazing devices with great capabilities. Fundamentally, though, the way they work is basically these two parallel cylinders with pistons. They're working in opposite in conjunction, where one piston is drawing back, creating a vacuum, drawing in concrete from the hopper, and the other parallel cylinder pushing forward, driven by hydraulics, basically driving the concrete in the chamber through a valve and then up to the pipe. And then through this process, you're able to push the concrete out at great pressures, so therefore at great heights. And then this can move with actually very rapid cycles. So if you happen to be on a concrete high-rise job and you'd be walking around the job site, you'll become very familiar with the usual, the hammering sounds of the sounds associated with this concrete pump working as it moves the dense viscous material up through the pipes up to where the working deck. This is a diagram that's been around for a long while, and it's basically a guide to basically determining what your pump pressure is and thereby sizing your concrete pump. There's a lot of information in here. I won't go belabor it too much, but basically you have output on this vertical axis here in either cubic meter per hour or yards per hour. You have in these radial lines here, you got pipe diameter. Over here you have a concrete slump. So obviously the slump of the mix you're pushing through has an impact. And then here's proportional length. So obviously the length of the pipe that you're pumping through. This proportional length considers 90-degree bends, as well as it considers like height, where you're adding basically the total length of the pipe, but then you're also adding in bars to represent vertical height. And then as you come around this graph, you would determine the pump pressure, and then obviously determine the rating of the machine power. To kind of show how this all works and different things that affect the pump pressure, obviously machine power, the output or cubic yards per hour, pipe diameter, the length of the pipe, including provisions for bends, the slump, and the height difference. So for instance, this graph right here, just work through, it's slightly different from the previous one, but it gives an example to how the rate of the machine output or yardage of material affects the actual pump pressure. So for instance, you start off here blue with the 60 yards per hour, and you move over to this line right here with the intersecting line with a 5-inch, and then you come down over here to the proportional feet, which is like 200 feet, and then you come over here to the slump, which is basically saying a 4-inch slump. It comes up here and you calculate 171 PSI in terms of pump pressure. But if you were to try to do 180 yards per hour, you'd see you'd be way up over here. You intersect the 5-inch line, you come down over here to the 200 feet, and then come over here to your 4-inch slump, and you come back over here, you're calculating 614. So I guess what I'm trying to say is the rate at which you push concrete through the system is going to definitely impact the pressure that the pump has to push. And then, of course, people still use those old style graphs, but there are online tools available. This is an online tool available from Putzmeister, where you can determine machine power required, and you enter some values and you calculate the power required, or you can enter the power you have and it can calculate, you put in your output and your power, and it can tell you the pressure or vice versa. Just following these simple equations here. And then this here can delivery line pressure. So again, you can enter this value here, which is a function of slump. As a fact, you can basically check your water cement ratio, either less than or greater than 0.42, adjusted pipe length, pipe diameter, output, and so on. And you can calculate what your delivery pressure is, or bar. So there's some very simple but very useful online tools available from manufacturers. Obviously, you got a pump, but you need to push it through something. So sizing the pipes. Pipe is that you're pushing your material through is very much driven by those project parameters that we were just talking about. And the wall thickness required for that pipe is a function of that calculated pressure. And you have a simple equation here. The pipe that we utilize is typically hardened steel, and we're with a safety factor of 2.0. The steel is specialty fabricated. They come in lengths of 1 to 3 meters. They have special flange ends, and they're either bolt connected or quick release couplings. But it's expensive, and we definitely want to get reuse out of it. But because the pipe is withstanding great pressures and cyclical loading and very abrasive material, it definitely has a life expectancy. So it requires continual inspection, visual and wall thickness measurements, and then most importantly, tracking the yardage you're pushing through that pipe. And then if you're building assemblies, obviously you want to be putting in your newer pipe with less wear at the high pressure areas near the pump, because that's where the highest pressures are. As you move further away, the pressures drop. To give an idea of life expectancy, half-inch wall pipe that we used, for instance, at the Vista project, which I'll be talking about, has about 120,000 cubic yard life, versus a quarter-inch wall would have about a 60,000 cubic yard life expectancy. Now you got your pipe, you got to secure it. You're moving a very dense, viscous material, with high pressures. And so obviously if you're changing direction, there's going to be associated forces with it. So typically what we do is we have stanchions and props that are basically securing this along the way. And then as we turn 90 degrees, we have these thrust blocks, basically casting the whole corner into a blob of concrete. And then as we turn vertical, we quite often add extensions to the concrete core, and again, to capture all this and to withstand all these forces. And then obviously now you got your pump, you got your pipe, you got you basically can deliver your concrete up into your deck. But when you're done, you've got a whole line of pipe that's filled with concrete. Now what do you do? So typically the process of purging out the concrete line after the completion of a pour is done by a sponge pig. So these examples right here. So upon the completion of the pour, they basically insert this and then insert special fittings. They basically attach the end of at the top of the working deck with a compressor, and then utilizing a compressor that's up there, basically push this assembly back down through the pipe. There's close communication between the working deck and the operator. At the time they're starting to they basically pressurize the system with air. They basically switch this gate here from basically the pump to a discharge, and then it basically would deposit the concrete that's in the line into a waiting concrete truck. And you notice the end here, it's got this cage to be able to capture the pig. Obviously, careful coordination between the guys in the deck and the guy at the pump is critical. Basically, if lack of communication could cause a lot of safety or serious life safety issues, or potentially air pockets or rock pockets or all sorts of problems. So basically, only trained personnel would be doing this. As a side note, for high rises, we found that certain mixes are more problematic to pump, but also problematic to clean out. So the EMOD mixes, high modulus mixes, were noted to be problematic. So what we've been doing, or have done in the past, is actually have to purge the EMOD mix out up on through purge the whole line out into a waiting concrete bucket up on the deck with a traditional low strength mix. Once that was all done, then do the pneumatic sponge pig purging that way, and then bring the EMOD mix that was in the lines on the bucket back down by crane. Just to avoid problems. Logistics. So you got you got your pump. Now you got to figure out a way where to put it to make sure you got a efficient and service to it. So this is a project from we're just recently finishing up. Basically, just showing the access by the road, and basically we've got the concrete pump over here. We've got two concrete trucks staged, and we've got the ability to stage more trucks here. So fundamentally, placing the pump, you need to place it with easy access to a public road, with room for at least 2 trucks at the pump at all times, with room for staging additional trucks nearby. And also, just again, for good pumping operations, we found it's good practice to have around 10% or even 15% horizontal run between the pump and where you go vertical. That kind of acts as to help to reduces the peak pressures that the pump sees and shows better operation. So just basically a operational experience. So now you got to figure out how you're going to actually deposit the concrete up on the working deck. So there's a number of different ways. One of the ways we typically use, one of the tools we typically use is a concrete placing boom. Basically, it's an articulating arm that can expand out and reach a working radius. These arms can have great radiuses or great reach. They're between 24 and 42 meters. That's 137 feet. This diagram here is showing a concrete placing boom on a tower and showing its reach on a given job. So it's a tremendous reach. And obviously, determining how you're going to deposit the concrete and the engineering means to do that can be quite involved. This is actually from a submitted drawing that we created for a project that's just currently finishing up on, and we full engineer drawings stamped and whatnot, and quite a bit of planning involved. This particular installation involved an RS-850 tower with a placing boom placed on top of it, and this is showing the different stages of construction. So as the project advanced, this placing boom initially was supported on 2 levels and then shored down to grade. And then as the project progressed, we jumped or climbed this placing boom up and successively added shoring until the point where this placing boom tower was entirely supported by shoring and reshoring. The cool thing about this placing boom, and I got some more pictures, is this is an RS-850 Putzmeister tower. It's got a hydraulic climbing capabilities. So in other words, it can basically climb itself up without the need of a tower crane, and basically can climb itself with the placing boom attached. So compared to the traditional or older style lattice placing boom towers that would require a tower crane to pick off the placing boom, put it on the ground, then grab the placing boom tower, climb it up, and then bring the placing boom tower back on, tying up tower crane. This is a pretty cool new technology and new development that's been introduced in recent years. Some more diagrams, just basically of the shoring towers, and I got it. So anyways, shoring of the placing boom tower all the way down and whatnot, and basically description of how the placing boom is wedged at the upper and lower. And then this is some pictures of how it's wedged. Again, we've got the gravity being taken out here. We got wedges up here for the upper wedge, and this is that hydraulic pawl that can climb the placing boom tower. And then another place we put it would be on top of the core. So this is a core shop drawing from Wanda Vista. Here's a cruciform base, which we can mount the placing boom tower. Working with DOCA, we would share with them the placing boom equipment and the loads and geometry they would design for. Here's a section view showing the placing boom on top of the core. And then here's a detail showing how it's attached, and this is showing the bolts right here. And then here's a picture of the Wanda Tower being built. And so you can see this is an early part of the project. So we've got the west core here with the placing boom on top of the core. Here's the east core here, another placing boom right over here. And then because we couldn't reach all the way, we had an RS-850 tower over here. And we were able to basically move this placing boom over to this one as needed as we went up. And here's a picture showing my colleagues out there moving the placing boom on top of the RS-850. And then pumpable concrete. I'm sure my colleagues will be talking about this, but basically you got this great pumping system. How do you get the concrete to where it needs to go? To get it together, but you need to have the material that can be pushed where it needs to go. So a critical thing for success is we need to prime the system with a grout to create a boundary layer to reduce the drag or friction. We need to have adequate concrete paste to suspend that aggregate in that concrete mixture. So that's really, really important. Our aggregate, we need to have consistent grading. The size is important. We can absolutely not have aggregate that's larger than 1/3 the pipe diameter. The shape of the aggregate is very important. Obviously, angular is causes more friction, could be more problematic versus round. we've noticed that fine aggregates are natural are better than artificial. I think it's the associated with the angle. And then pumpability is definitely related to fineness modulus. In other words, use of finer fines can be an issue. Aggregate, lightweight aggregate and that basically need to make sure it's properly saturated. If the aggregate is not, it can absorb water and reduce the available paste. So pre-soaking is critical. Slump, as we talked about earlier, slump is critical. Higher slump are better. And then admixtures. Fundamentally, any admixture that increases workability usually improves pumpability. So your super plasticizers are very beneficial, and your supplementary cementitious, your fly ash and slag, those definitely are noted to improve pumpability. And with that, I can share a video. And this is a drone footage from the Vista project taken about 2 years ago. This was level 59. And as we're zooming up, you can see the concrete placement with our concrete placing boom right here, depositing concrete that's being pumped from basically about 650 feet down below. So showing a very efficient and easy ability to move concrete to where it needs to go, and basically allows us to keep our rapid 3-day cycles. So with that, I am open for any questions.
Thank you, Eamonn. So this is the time normally you get an applause, so let's assume you get a virtual applause now from our audience. If there are questions, please feel free to use the question and answer button. So you get the question, you can type the question in there, and then either Matt or me will present the question to Eamonn. But at this point, I don't really see any questions opening up, so maybe I'll start, Eamonn. Based on your experience in constructing all of these magnificent buildings and towers and everything else, what's the biggest challenge?
Basically, ensuring we have pumpable concrete. Definitely if we are not basically pumping concrete consistently at the yards, there's a lot of people who will be standing around idle, and that's a huge problem for the schedule, and it's hugely expensive for the contractor. So ensuring that the mix is pumpable is definitely, I guess it becomes a problem when it is a problem. And if it becomes at the forefront of everybody's mind immediately. For this particular project, right there, we were probably pushing through between 54 and 65 yards per hour, and having basically pump pressures of 120 to 180. If we weren't able to do that for some reason, whether the pump broke down or the concretes were not cooperative, that would be a really big problem, and it would be a problem that have to be addressed right away.
Eamonn, there's one question off the Q&A. What precautions need to be assured? What precautions need to assure pumping does not adversely impact air content?
Obviously, air is a very important issue, and generally it's been observed that loss of air can absolutely occur. So definitely doing tests, when you're designing your mix and testing it to ensure that you've got stability of air in your mix. So quite often, the air might be dosed at a higher percentage than what's actually required, and then and then taking samples and testing for air at the actual depositing is critical. So I think basically it all starts with the proper design of the mix and trial testing of the mix to ensure that it's actually going to work.
Then we got another question. Any experience in pumping UHPC, ultra high performance concrete?
When I say ultra high performance, that would be the stuff with the fibers and stuff like that. We've only done we've pumped some obviously various fibers and slab-on grade applications, polypropylene, and we've done the steel fibers as well. Obviously, we found that with the steel ones with heavier dosage, that was potentially a challenge, but obviously with the super plasticizers and slump modification, we were able to get it to work. But no, we have not tried to pump ultra high performance.
We got one last one, and that's the last one we'll handle, then we need to move on. Have you measured the hardened properties of concrete exactly at the beginning and at the end of the pipeline and compared the results?
We've definitely taken samples at delivery on the site and measured air and measured unit weight as well as slump or spread, and then measured them again at deposit and ensuring, because quite often that project specs may require that, and have to adjust the mix design appropriately because of that. So because again, if you don't have the air where you're in the actual deposit of concrete, from the design team's perspective, that's a problem. So yes, we have done that.